Hi grade 12s. Welcome to your final video for acid and base equilibrium. Today's focus will be on titration curves for acids and bases. As you learned in Chemistry 20, a pH curve is a graph that shows the change of pH versus the volume of titrant added in an acid-base titration. pH curves are easily recognizable because they have a characteristic shape. When we look at these curves, we should be able to determine the value of the solution's pH when an acid-base reaction reaches its equivalence point. This would allow us to select an appropriate indicator to use for a titration. In a titration, the end point is the point in a titration when the chemist stops adding titrant. The chemist stops adding titrant because they observe a color change. Endpoints are easy to detect because the pH changes quickly. The endpoint is not the same thing as the equivalence point. The equivalence point is the point in the reaction when equivalent amounts of the reactants have been combined. Notice how pH curves have three different regions. They begin with a gradual pH change, followed by a rapid change, and then a slow change in pH at the end. The nearly flat regions of the titration curve, where the pH changes very little, are called the buffering regions. In the buffering region shown here, the strong acid being added immediately reacts with excess hydroxide ions in the solution. The acid and hydroxide end up forming water, so the solution still contains mostly water and hydroxide ions. The pH leveling effect finally fails near the equivalence point, when the hydroxide ions are almost completely consumed. Once these hydroxide ions are mostly consumed, then small additions of acid will begin to have a greater effect on the pH of the solution. This is when the pH will change more quickly. The inflection point, or the point where the graph changes direction, is the equivalence point of the reaction. After the equivalence point, the titration curve enters a new buffering region where the solution is already acidic, so small additions of acid don't affect the pH very much. Here is a titration curve for a weak acid being titrated with a strong base. Notice the characteristic shape, the buffering regions, and that the equivalence point is at 40 milliliters of base added. Because it is a strong base and a weak acid, the expected pH at the equivalence point would be greater than 7. In this pH curve, a weak base is titrated with a strong acid. Because it is a strong acid and a weak base, the expected pH at the equivalence point would be less than 7. Polyprotic acids are able to lose more than one proton, and polyprotic bases are able to gain more than one proton. The titration curves that we have looked at so far are monoprotic acids. The pH curves for diprotic or triprotic acids and bases look different. Here is a titration curve for sodium carbonate being titrated with hydrochloric acid. Sodium carbonate is ionic, and so it dissociates into sodium and carbonate ions. Carbonate ions are able to accept 2 protons, and so they are polyprotic bases. For each proton that can be accepted, there is an equivalence point. Here you can see how the different components come together. The HCl is a strong acid, so the entities that are present would be hydronium ions and chloride ions. Sodium carbonate would dissociate into sodium and carbonate ions. Water is also present. It turns out that the strongest acid would be hydronium ions and the strongest base would be the carbonate ions. At the first equivalence point, the carbonate ions have been consumed and hydrogen carbonate ions are present. These are the entities that are present after the first equivalence point. Hydrogen carbonate ions are reacting with the hydronium ions now to produce carbonic acid. At the second equivalence point, all of the hydrogen carbonate ions will have reacted. As we add more hydronium ions after the second equivalence point, the impact on the pH will be reduced because the curve will be in its buffering region. Here are some examples of the polyprotic entities that you may encounter. As we add more hydrogens to polyprotic bases, or remove hydrogens from polyprotic acids, the strength of them greatly decreases. You can see this trend by observing where they are located on your acid-base table. Take a look at this titration curve for phosphoric acid being titrated with sodium hydroxide. Is this the titration curve that you would expect? By looking at the pH curve, you may expect that the polyprotic acid only loses 2 protons. This does not agree with the molecular formula for phosphoric acid, which has 3 hydrogens. There is a simple explanation for this, but it does require some analysis of the system. Begin with the original acid and base. The reaction between phosphoric acid and hydroxide ions results in the production of water and dihydrogen phosphate ions. In turn, these ions will react with hydroxide ions to form hydrogen phosphate ions. The hydrogen phosphate ions are very weak acids, so the pH will rise abruptly with the addition of more hydroxide ions. It turns out the hydrogen phosphate ions are such weak acids that they don't quantitatively lose protons to hydroxide ions. This is why a third equivalence point is not observed. As a general rule, only quantitative reactions produce detectable equivalence points in an acid-base titration. Because polyprotic acids and bases get weaker and weaker as they lose and gain protons, there are almost no reactions that have more than 2 definite endpoints. For stoichiometric purposes, Bronsted-Lowry equations for polyprotic acids and bases can be combined to form one overall reaction. If strong acids and bases are used, you should expect an equivalence point at a pH of 7. This is because they create water as a product, which is neutral. Not all titrations involve strong acids and bases, though. You should learn some general trends for the type of curve that will be expected. The equivalence point pH for a strong acid and strong base reaction is 7. The equivalence point for a strong acid-weak base reaction is less than 7. The equivalence point for a weak acid-strong base reaction is greater than 7. We do not have a generic curve for weak acids and weak bases. This is because they do not have a detectable equivalence point because they are not usually quantitative. Now that you have finished your final lesson, you may begin preparing for the unit exam.